Chapter 8, Part 5 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 8, Part 5. Power-off accuracy approaches. Power-off accuracy approaches are approaches and landings made by gliding with the engine idling through a specific pattern to a touchdown beyond and within 200 feet of a designated line or mark on the runway. The objective is to instill in the pilot the judgment and procedures necessary for accurately flying the airplane without power to a safe landing. The ability to estimate the distance an airplane will glide to a landing is the real basis of all power-off accuracy approaches and landings. This will largely determine the amount of maneuvering that may be done from a given altitude. In addition to the ability to estimate distance, it requires the ability to maintain the proper glide while maneuvering the airplane. With experience and practice, altitudes up to approximately 1,000 feet can be estimated with fair accuracy. While above this level, the accuracy and judgment of height above the ground decreases, since all features tend to merge. The best aid in perfecting the ability to judge height above this altitude is through the indications of the altimeter and associating them with the general appearances of the Earth. The judgment of altitude in feet, hundreds of feet, or thousands of feet is not as important as the ability to estimate gliding angle and its resultant distance. The pilot who knows the normal glide angle of the airplane can estimate with reasonable accuracy the approximate spot along a given ground path at which the airplane will land, regardless of altitude. The pilot, who also has the ability to accurately estimate altitude, can judge how much maneuvering is possible during the glide, which is important to the choice of landing areas in an actual emergency. The objective of a good final approach is to descend at an angle that will permit the airplane to reach the desired landing area and at an airspeed that will result in minimum floating just before touchdown. To accomplish this, it is essential that both the descent angle and the airspeed be accurately controlled. Unlike a normal approach, when the power setting is variable, on a power-off approach the power is fixed at the idle setting. Pitch attitude is adjusted to control the airspeed. This will also change the glide or descent angle. By lowering the nose to keep the approach airspeed constant, the descent angle will steepen. If the airspeed is too high, raise the nose. And when the airspeed is too low, lower the nose. If the pitch attitude is raised too high, the airplane will settle rapidly due to the slow airspeed and insufficient lift. For this reason, never try to stretch a glide to reach the desired landing spot. Uniform approach patterns such as 90-degree, 180-degree, or 360-degree power-off approaches are described further in this chapter. Practice in these approaches provides the pilot with the basis on which to develop judgment in gliding distance and in planning an approach. The basic procedure in these approaches involves closing the throttle at a given altitude and gliding to a key position. This position, like the pattern itself, must not be allowed to become the primary objective. It is merely a convenient point in the air from which the pilot can judge whether the glide will safely terminate at the desired spot. The selected key position should be one that is appropriate for the available altitude and the wind condition. From the key position, the pilot must constantly evaluate the situation. It must be emphasized that, although accurate spot touchdowns are important, safe and properly executed approaches and landings are vital. The pilot must never sacrifice a good approach or landing just to land on the desired spot. 90-degree power-off approach. The 90-degree power-off approach is made from the base leg and requires only a 90-degree turn-on to final approach. The approach path may be varied by positioning the base leg closer to or farther out from the approach end of the runway according to wind conditions. See Figure 8-25. The glide from the key position on the base leg through the 90-degree turn to the final approach is the final part of all accuracy landing maneuvers. The 90-degree power-off approach usually begins from a rectangular pattern at approximately 1,000 feet above the ground or at normal traffic pattern altitude. The airplane should be flown onto a downwind leg at the same distance from the landing surface as in a normal traffic pattern. The before-landing checklist should be completed on the downwind leg, including extension of the landing gear if the airplane is equipped with retractable gear. After a medium bank turn onto the base leg is completed, the throttle should be retarded slightly and airspeed allowed to decrease to the normal base leg speed. See Figure 8-26. On the base leg, the airspeed, wind, drift correction, and altitude should be maintained while proceeding to the 45-degree key position. At this position, the intended landing spot will appear to be on a 45-degree angle from the airplane's nose. The pilot can determine the strength and direction of the wind from the amount of crab necessary to hold desired ground track on the base leg. This will help in planning the turn onto final approach and in lowering the correct amount of flaps. At the 45-degree key position, the throttle should be closed completely. The propeller control, if equipped, advance to the full increase RPM position and altitude maintained until the airspeed decreases to the manufacturer's recommended glide speed. In the absence of recommended speed, use 1.4 VSO. When the airspeed is attained, the nose should be lowered to maintain the gliding speed and controls retrimmed. The base to final turn should be planned and accomplished so that upon rolling out of the turn, the airplane will be aligned with the runway centerline. When on final approach, the wing flaps are lowered and the pitch attitude adjusted as necessary to establish the proper descent angle and airspeed. 1.3 VSO. Then the controls retrimmed. Slight adjustments in pitch attitude or flap settings may be necessary to control the glide angle and airspeed. However, never try to stretch the glide or retract the flaps to reach the desired landing spot. The final approach may be made with or without the use of slips. After the final approach glide has been established, full attention is then given to making a good, safe landing rather than concentrating on the selected landing spot. The base leg position and the flap setting already determined the probability of landing on the spot. In any event, it is better to execute a good landing 200 feet from the spot than to make a poor landing precisely on the spot. 180-degree power-off approach. The 180-degree power-off approach is executed by gliding with the power off from a given point on a downwind leg to a pre-selected landing spot. See Figure 8-27. It is an extension of the principles involved in the 90-degree power-off approach just described. Its objective is to further develop judgment in estimating distance and glide ratios, in that the airplane is flown without power from a higher altitude and through a 90-degree turn to reach the base leg position at a proper altitude for executing the 90-degree approach. The 180-degree power-off approach requires more planning and judgment than the 90-degree power-off approach. In the execution of 180-degree power-off approaches, the airplane is flown on a downwind heading parallel to the landing runway. The altitude from which this type of approach should be started will vary with the type of airplane, but it should usually not exceed 1,000 feet above the ground, except with large airplanes. Greater accuracy in judgment and maneuvering is required at higher altitudes. When abreast of or opposite the desired landing spot, the throttle should be closed and altitude maintained while decelerating to the manufacturer's recommended glide speed, or 1.4 VSO. The point at which the throttle is closed is the downwind key position. The turn from the downwind leg to the base leg should be a uniform turn with a medium or slightly steeper bank. The degree of bank and amount of this initial turn will depend upon the glide angle of the airplane and the velocity of the wind. Again, the base leg should be positioned as needed for the altitude, or wind condition. Position the base leg to conserve or dissipate altitude so as to reach the desired landing spot. The turn onto the base leg should be made with an altitude high enough and close enough to permit the airplane to glide to what would normally be the base key position in a 90-degree power-off approach. Although the key position is important, it must not be overemphasized nor considered as a fixed point on the ground. Many inexperienced pilots may gain a conception of it as a particular landmark, such as a tree, crossroad, or other visual reference, to be reached at a certain altitude. This will result in a mechanical conception and leave the pilot at a total loss at any time such objects are not present. Both altitude and geographical location should be varied as much as is practical to eliminate any such conception. After reaching the base key position, the approach and landing are the same as in the 90-degree power-off approach. 360-degree power-off approach. The 360-degree power-off approach is one in which the airplane glides through a 360-degree change of direction to the pre-selected landing spot. The entire pattern is designed to be circular, but the turn may be shallowed, steepened, or discontinued at any point to adjust the accuracy of the flight path. The 360-degree approach is started from a position over the approach end of the landing runway or slightly to the side of it, with the airplane headed in the proposed landing direction and the landing gear and flaps retracted. See Figure 8-28. It is usually initiated from approximately 2,000 feet or more above the ground, where the wind may vary significantly from that of lower altitudes. This must be taken into account when maneuvering the airplane to a point from which a 90-degree or 180-degree power-off approach can be completed. After the throttle is closed over the intended point of the landing, the proper glide speed should immediately be established and a medium banked turn may be in the desired direction so as to arrive at the downwind key position opposite the intended landing spot. At or just beyond the downwind key position, the landing gear may be extended, if the airplane is equipped with retractable gear. The altitude at the downwind key position should be approximately 1,000 to 1,200 feet above the ground. After reaching that point, the turn should be continued to arrive at a base leg key position at an altitude of about 800 feet above the terrain. Flaps may be used at this position as necessary, but full flaps should not be used until established on the final approach. The angle of bank can be varied as needed throughout the pattern to correct for wind conditions and to align the airplane with the final approach. The turn to final should be completed at a minimum altitude of 300 feet above the terrain. Common errors in performance of power-off accuracy approaches are downwind leg too far from the runway landing area, overextension of downwind leg resulting from tailwind, inadequate compensation for wind drift on base leg, skidding turns in an effort to increase gliding distance, failure to lower landing gear in retractable gear airplanes, attempting to stretch the glide during undershoot, premature flap extension, landing gear extension, use of throttle to increase the glide instead of merely clearing the engine, forcing the airplane onto the runway in order to avoid overshooting the designated landing spot. Emergency approaches and landings. Simulated. From time to time on dual flights, the instructor should give simulated emergency landings by retarding the throttle and calling simulated emergency landing. The objective of these simulated emergency landings is to develop the pilot's accuracy, judgment, planning, procedures, and confidence when little or no power is available. A simulated emergency landing may be given with the airplane in any configuration. When the instructor calls simulated emergency landing, the pilot should immediately establish a glide attitude and ensure the flaps and landing gear are in the proper configuration for the existing situation. When the proper glide speed is attained, the nose should then be lowered and the airplane trimmed to maintain that speed. A constant gliding speed should be maintained because variations of gliding speed nullify all attempts at accuracy and judgment of gliding distance and the landing spot. The many variables, such as altitude, obstruction, wind direction, landing surface and gradient, and landing distance requirements of the airplane will determine the pattern and approach procedures to use. Utilizing any combination of normal gliding maneuvers, from wings level to spirals, the pilot should eventually arrive at the normal key position at a normal traffic pattern altitude for the selected landing area. From this point on, the approach should be as nearly as possible to the normal power-off approach. See Figure 8-29. With the greater choice of fields afforded by higher altitudes, the inexperienced pilots may be inclined to delay making a decision, and with considerable altitude in which to maneuver, errors in maneuvering and estimation of glide distance may develop. All pilots should learn to determine the wind direction and estimate its speed from the windsock at the airport, smoke from factories or houses, dust, brush fires, and windmills. Once a field has been selected, the student pilot should always be required to indicate it to the instructor. Normally, the student should be required to plan and fly a pattern for landing on the field first elected until the instructor terminates the simulated emergency landing. This will give the instructor an opportunity to explain and correct any errors. It will also give the student an opportunity to see the results of the errors. However, if the student realizes during the approach that a poor field has been selected, one that would obviously result in disaster if a landing were to be made, and there is a more advantageous field within a gliding distance, a change to a better field should be permitted. The hazards involved in these last-minute decisions, such as excessive maneuvering at very low altitudes, should be thoroughly explained by the instructor. Slipping the airplane, using flaps, varying the position of the base leg, and varying the turn onto final approach should be stressed as ways of correcting for misjudgment of altitude and glide angle. Eagerness to get down is one of the most common faults of inexperienced pilots during simulated emergency landings. In giving way to this, they forget about the speed and arrive at the edge of the field with too much speed to permit a safe landing. Too much speed may be just as dangerous as too little. It results in excessive floating and overshooting the desired landing spot. It should be impressed on the students that they cannot dive at a field and expect to land on it. During all simulated emergency landings, the engine should be kept warm and cleared. During a simulated emergency landing, either the instructor or the student should have complete control of the throttle. There should be no doubt as to who has control, since many near accidents have occurred from such misunderstandings. Every simulated emergency landing approach should be terminated as soon as it can be determined whether a safe landing could have been made. In no case should it be continued to a point where it creates an undue hazard or an annoyance to persons or property on the ground. In addition to flying the airplane from the point of simulated engine failure to where a reasonable safe landing could be made, the student should also be taught certain emergency cockpit procedures. The habit of performing these cockpit procedures should be developed to such an extent that when the engine failure actually occurs, the student will check the critical items that would be necessary to get the engine operating again while selecting a field and planning an approach. Combining the two operations, accomplishing emergency procedures and planning and flying the approach, will be difficult for the student during the early training in emergency landings. There are definite steps and procedures to be followed in a simulated emergency landing. Although they may differ somewhat from the procedures used in an actual emergency, they should be learned thoroughly by the student and each step called out to the instructor. The use of a checklist is strongly recommended. Most airplane manufacturers provide a checklist of the appropriate items. See Figure 8-30. Critical items to be checked should include the position of the fuel tank selector, the quantity of fuel in the tank selected, the fuel pressure gauge to see if the electric fuel pump is needed, the position of the mixture control, the position of the magneto switch, and the use of carburetor heat. Many actual emergency landings have been made and later found to be the result of the fuel selector valve being positioned to an empty tank while the other tank had plenty of fuel. It may be wise to change the position of the fuel selector valve even though the fuel gauge indicates fuel in all tanks, because fuel gauges can be inaccurate. Many actual emergency landings could have been prevented if the pilots had developed the habit of checking these critical items during flight training to the extent that it carried over into later flying. Instruction in emergency procedures should not be limited to simulated emergency landings caused by power failures. Other emergencies associated with the operation of the airplane should be explained, demonstrated, and practiced if practicable. Among these emergencies are such occurrences as fire in flight, electrical or hydraulic system malfunctions, unexpected severe weather conditions, engine overheating, imminent fuel exhaustion, and the emergency operation of airplane systems and equipment. End Chapter 8, Part 5. Recording by Dale Latham.
Chapter 8, Part 6 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Ilver. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Faulty Approaches and Landings. Low Final Approach. When the base leg is too low, insufficient power is used, landing flaps are extended prematurely, or the velocity of the wind is misjudged. Sufficient altitude may be lost, which will cause the airplane to be well below the proper final approach path. In such a situation, the pilot would have to apply considerable power to fly the airplane at an excessively low altitude up to the runway threshold. When it is realized the runway will not be reached unless appropriate action is taken, power must be applied immediately to maintain the airspeed, while the pitch attitude is raised to increase lift and stop the descent. When the proper approach path has been intercepted, the correct approach attitude should be reestablished and the power reduced and a stabilized approach maintained. Figure 8-31. Do not increase the pitch attitude without increasing the power, since the airplane will decelerate rapidly and may approach the critical angle of attack and stall. Do not retract the flaps. This will suddenly decrease lift and cause the airplane to sink more rapidly. If there is any doubt about the approach being safely completed, it is advisable to execute an immediate go-around. High final approach. When the final approach is too high, lower the flaps as required. Further reduction in power may be necessary, while lowering the nose simultaneously to maintain approach airspeed and steepen the approach path. Figure 8-32. When the proper approach path has been intercepted, adjust the power as required to maintain a stabilized approach. When steepening the approach path, however, care must be taken that the descent does not result in an excessively high sink rate. If a high sink rate is continued close to the surface, it may be difficult to slow to a proper rate prior to ground contact. Any sink rate in excess of 800 to 1,000 feet per minute is considered excessive. A go-around should be initiated if the sink rate becomes excessive. Slow final approach. When the airplane is flown at a slower than normal airspeed on the final approach, the pilot's judgment of the sink rate, descent, and the height of roundout will be difficult. During an excessively slow approach, the wing is operating near the critical angle of attack, and, depending on the pitch attitude changes and control usage, the airplane may stall or sink rapidly, contacting the ground with a hard impact. Whenever a slow speed approach is noted, the pilot should apply power to accelerate the airplane and increase the lift to reduce the sink rate and to prevent a stall. This should be done while still at a high enough altitude to establish the correct approach airspeed and attitude. If too slow and too low, it is best to execute a go-around. Use of power. Power can be used effectively during the approach and round-out to compensate for errors in judgment. Power can be added to accelerate the airplane to increase lift without increasing the angle of attack. Thus, the descent can be slowed to an acceptable rate. If the proper landing attitude has been attained and the airplane is only slightly high, the landing attitude should be held constant and sufficient power applied to help ease the airplane onto the ground. After the airplane has touched down, it will be necessary to close the throttle so the additional thrust and lift will be removed and the airplane will stay on the ground. High round-out. Sometimes when the airplane appears to temporarily stop moving downward, the round-out has been made too rapidly and the airplane is flying level, too high above the runway. Continuing the round-out would further reduce the airspeed, resulting in an increase in angle of attack to the critical angle. This would result in the airplane stalling and dropping hard onto the runway. To prevent this, the pitch attitude should be held constant until the airplane decelerates enough to again start descending. Then the round-out can be continued to establish the proper landing attitude. This procedure should only be used when there is adequate airspeed. It may be necessary to add a slight amount of power to keep the airspeed from decreasing excessively and to avoid losing lift too rapidly. Although the back elevator pressure may be relaxed slightly, the nose should not be lowered any perceptible amount to make the airplane descend when fairly close to the runway, unless some power is added momentarily. The momentary decrease in lift that would result from lowering the nose and decreasing the angle of attack may be so great that the airplane might contact the ground with the nose wheel first, which could collapse. When the proper landing attitude is attained, the airplane is approaching a stall because the airspeed is decreasing and the critical angle of attack is being approached, even though the pitch attitude is no longer being increased. Figure 8-33. It is recommended that a go-around be executed anytime it appears the nose must be lowered significantly or that the landing is in any other way uncertain. Late or rapid round-out. Starting the round-out too late or pulling the elevator control back too rapidly to prevent the airplane from touching down prematurely can impose a heavy load factor on the wing and cause an accelerated stall. Suddenly increasing the angle of attack and stalling the airplane during a round-out is a dangerous situation since it may cause the airplane to land extremely hard on the main landing gear and then bounce back into the air. As the airplane contacts the ground, the tail will be forced down very rapidly by the back elevator pressure and by inertia acting downward on the tail. Recovery from this situation requires prompt and positive application of power prior to occurrence of the stall. This may be followed by a normal landing if sufficient runway is available. Otherwise, the pilot should execute a go-around immediately. If the round-out is late, the nose wheel may strike the runway first, causing the nose to bounce upward. No attempt should be made to force the airplane back onto the ground. A go-around should be executed immediately. Floating during round-out. If the airspeed on final approach is excessive, it will result in the airplane floating. Figure 8-34. Before the touchdown can be made, the airplane may be well past the desired landing point and the available runway may be insufficient. When diving in an airplane on final approach to land at the proper point, there will be an appreciable increase in airspeed. The proper touchdown attitude cannot be established without producing an excessive angle of attack and lift. This will cause the airplane to gain altitude or balloon. Anytime the airplane floats, judgment of speed, height, and sink rate must be especially acute. The pilot must smoothly and gradually adjust the pitch attitude as the airplane decelerates to touchdown speed and starts to settle, so the proper landing attitude is attained at the very moment of touchdown. The slightest error in judgment and timing will result in either ballooning or bouncing. The recovery from floating will depend on the amount of floating and the effect of any crosswind, as well as the amount of runway remaining. Since prolonged floating utilizes considerable runway length, it should be avoided, especially on short runways or in strong crosswinds. If the landing cannot be made on the first third of the runway, or the airplane drifts sideways, the pilot should execute a go-around. Ballooning during round-out. If the pilot misjudges the rate of sink during a landing and thinks the airplane is descending faster than it should, there is a tendency to increase the pitch attitude and angle of attack too rapidly. This not only stops the descent, but actually starts the airplane climbing. This climbing during the round-out is known as ballooning. Figure 8-35. Ballooning can be dangerous because the height above the ground is increasing and the airplane may be rapidly approaching a stalled condition. The altitude gained in each instance will depend on the airspeed or the speed with which the pitch attitude is increased. When ballooning is slight, a constant landing attitude should be held and the airplane allowed to gradually decelerate and settle onto the runway. Depending on the severity of ballooning, the use of throttle may be helpful in cushioning the landing. By adding power, thrust can be increased to keep the airspeed from decelerating too rapidly and the wings from suddenly losing lift. But throttle must be closed immediately after touchdown. Remember that torque can be created as power is applied. Therefore, it will be necessary to use rudder pressure to keep the airplane straight as it settles onto the runway. When ballooning is excessive, it is best to execute a go-around immediately. Do not attempt to salvage the landing. Power must be applied before the airplane enters a stalled condition. The pilot must be extremely cautious of ballooning when there is a crosswind present, because the crosswind correction may be inadvertently released or it may become inadequate. Because of the lower airspeed after ballooning, the crosswind affects the airplane more. Consequently, the wing will have to be lowered even further to compensate for the increased drift. It is imperative that the pilot make certain that the appropriate wing is downed and that directional control is maintained with opposite rudder. If there is any doubt or the airplane starts to drift, execute a go-around. Bouncing during touchdown. When the airplane contacts the ground with a sharp impact as the result of an improper attitude or an excessive rate of sink, it tends to bounce back into the air. Though the airplane's tires and shock struts provide some springing action, the airplane does not bounce like a rubber ball. Instead, it rebounds into the air because the wing's angle of attack was abruptly increased, producing a sudden addition of lift. Figure 8-36. The abrupt change in angle of attack is a result of the inertia instantly forcing the airplane's tail downward when the main wheels contact the ground sharply. The severity of the bounce depends on the airspeed at the moment of contact and the degree to which the angle of attack or pitch attitude was increased. Since a bounce occurs when the airplane makes contact with the ground before a proper touchdown attitude is attained, it is almost invariably accompanied by the application of excessive back elevator pressure. This is usually the result of the pilot realizing too late that the airplane is not in the proper attitude and attempting to establish it just as a second touchdown occurs. The corrective action for a bounce is the same as for ballooning and similarly depends on its severity. When it is very slight and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. In the event a very slight bounce is encountered while landing with a crosswind correction must be maintained while the next touchdown is made. Remember that since the subsequent touchdown will be made at a slower airspeed, the upwind wing will have to be lowered even further to compensate for drift. Extreme caution and alertness must be exercised anytime a bounce occurs, but particularly when there is a crosswind. Inexperienced pilots will almost invariably release the crosswind correction. When one main wheel of the airplane strikes the runway, the other wheel will touch down immediately afterwards, and the wings will become level. Then, with no crosswind correction, as the airplane bounces, the wind will cause the airplane to roll with the wind, thus exposing even more surface to the crosswind and drifting the airplane more rapidly. When a bounce is severe, the safest procedure is to execute a go-around immediately. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. The go-around procedure should be continued even though the airplane may descend and another bounce may be encountered. It would be extremely foolish to attempt a landing from a bad bounce, since airspeed diminishes very rapidly in the nose-high attitude, and a stall may occur before a subsequent touchdown could be made. Porpoising. In a bounced landing that is improperly recovered, the airplane comes in nose first, setting off a series of motions that imitate the jumps and dives of a porpoise, hence the name. Figure 8-37. The problem is improper airplane attitude at touchdown, sometimes caused by inattention, not knowing where the ground is, mistrimming, or forcing the airplane onto the runway. Ground effect decreases elevator control effectiveness and increases the effort required to raise the nose. Not enough elevator or stabilator trim can result in a nose-low contact with the runway and a porpoise develops. Porpoising can also be caused by improper airspeed control. Usually, if an approach is too fast, the airplane floats, and the pilot tries to force it on the runway when the airplane still wants to fly. A gust of wind, a bump in the runway, or even a slight tug on the control wheel will send the airplane aloft again. The corrective action for a porpoise is the same as for a bounce and similarly depends on its severity. When it is very slight and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. When a porpoise is severe, the safest procedure is to execute a go-around immediately. In a severe porpoise, the airplane's pitch oscillations can become progressively worse until the airplane strikes the runway nose first with sufficient force to collapse the nose gear. Pilot attempts to correct a severe porpoise with flight control and power inputs will most likely be untimely and out of sequence with the oscillations and only make the situation worse. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. Wheelbarrowing. When a pilot permits the airplane weight to become concentrated about the nose wheel during the takeoff or landing roll, a condition known as wheelbarrowing will occur. Wheelbarrowing may cause loss of directional control during the landing roll because braking action is ineffective, and the airplane tends to swerve or pivot on the nose wheel, particularly in crosswind conditions. One of the most common causes of wheelbarrowing during the landing roll is a simultaneous touchdown of the main and nose wheel with excessive speed, followed by the application of forward pressure on the elevator control. Usually the situation can be corrected by smoothly applying back elevator pressure. However, if wheelbarrowing is encountered and runway and other conditions permit, it may be advisable to promptly initiate a go-around. Wheelbarrowing will not occur if the pilot achieves and maintains the correct landing attitude, touches down at the proper speed, and gently lowers the nose wheel while losing speed on rollout. If the pilot decides to stay on the ground rather than attempt a go-around, or if directional control is lost, the throttle should be closed and the pitch attitude smoothly but firmly rotated to the proper landing attitude. Raise the flaps to reduce lift and to increase the load on the main wheels for better braking action. Hard landing. When the airplane contacts the ground during landings, its vertical speed is instantly reduced to zero. Unless provisions are made to slow this vertical speed and cushion the impact of touchdown, the force of contact with the ground may be so great that it could cause structural damage to the airplane. The purpose of pneumatic tires, shock-absorbing landing gears, and other devices is to cushion the impact and to increase the time in which the airplane's vertical descent is stopped. The importance of this cushion may be understood from the computation that a 6-inch freefall on landing is roughly equal to a 340 foot per minute descent. Within a fraction of a second, the airplane must be slowed from this rate of vertical descent to 0 without damage. During this time, the landing gear, together with some aid from the lift of the wings, must apply whatever force is needed to counteract the force of the airplane's inertia and weight. The lift decreases rapidly as the airplane's forward speed is decreased, and the force on the landing gear increases by the impact of touchdown. When the descent stops, the lift will be practically 0, leaving the landing gear alone to carry both the airplane's weight and inertia force. The load imposed at the instant of touchdown may easily be 3 or 4 times the actual weight of the airplane, depending on the severity of contact. Touchdown in a drift or crab. At times the pilot may correct for wind drift by crabbing on the final approach. If the round out and touchdown are made while the airplane is drifting or in a crab, it will contact the ground while moving sideways. This will impose extreme side loads on the landing gear, and, if severe enough, may cause structural failure. The most effective method to prevent drift in primary training airplanes is the wing-low method. This technique keeps the longitudinal axis of the airplane aligned with both the runway and the direction of motion throughout the approach and touchdown. There are 3 factors that will cause the longitudinal axis and the direction of motion to be misaligned during the touchdown: drifting, crabbing, or a combination of both. If the pilot has not taken adequate corrective action to avoid drift during a crosswind landing, the main wheel's tire tread offers resistance to the airplane's sideward movement in respect to the ground. Consequently, any sidewise velocity of the airplane is abruptly decelerated, with the results that the inertia force is as shown in Figure 8-38. This creates a moment around the main wheel when it contacts the ground, tending to overturn or tip the airplane. If the windward wingtip is raised by the action of this moment, all the weight and shock of landing will be borne by one main wheel. This could cause structural damage. Not only are the same factors present that are attempting to raise a wing, but the crosswind is also acting on the fuselage surface behind the main wheels, tending to yaw, weather vane the airplane into the wind. This often results in a ground loop. Ground loop. A ground loop is an uncontrolled turn during ground operation that may occur while taxiing or taking off, but especially during the after-landing roll. Drift or weather vaning does not always cause a ground loop, although these things may cause the initial swerve. Careless use of the rudder, or an uneven ground surface, or a soft spot that retards one main wheel of the airplane may also cause a swerve. In any case, the initial swerve tends to make the airplane ground loop, whether it is a tail wheel or a nose wheel type. Figure 8-39. Nose wheel type airplanes are somewhat less prone to ground loop than tail wheel type airplanes. Since the center of gravity, CG, is located forward of the main landing gear on these airplanes, anytime a swerve develops, centrifugal force acting on the CG will tend to stop the swerving action. If the airplane touches down while drifting or in a crab, the pilot should apply aileron toward the high wing and stop the swerve with the rudder. Brakes should be used to correct for turns or swerves only when the rudder is inadequate. The pilot must exercise caution when applying corrective brake action because it is very easy to over-control and aggravate the situation. If brakes are used, sufficient brake should be applied on the low wing wheel outside of the turn to stop the swerve. When the wings are approximately level, the new direction must be maintained until the airplane has slowed to taxi speed or has stopped. In nose wheel airplanes, a ground loop is almost always a result of wheelbarrowing. The pilot must be aware that even though the nose wheel type airplane is less prone than the tail wheel type airplane, virtually every type of airplane, including large multi-engine airplanes, can be made to ground loop when sufficiently mishandled. Wing rising after touchdown. When landing in a crosswind, there may be instances when a wing will rise during the after-landing roll. This may occur whether or not there is a loss of directional control, depending on the amount of crosswind and the degree of corrective action. Anytime an airplane is rolling on the ground in a crosswind condition, the upwind wing is receiving a greater force from the wind than the downwind wing. This causes a lift differential. Also, as the upwind wing rises, there is an increase in the angle of attack, which increases lift on the upwind wing, rolling the airplane downwind. When the effects of these two factors are great enough, the upwind wing may rise even though directional control is maintained. If no correction is applied, it is possible that the upwind wing will rise sufficiently to cause the downwind wing to strike the ground. In the event a wing starts to rise during the landing roll, the pilot should immediately apply more aileron pressure toward the high wing and continue to maintain direction. The sooner the aileron is applied, the more effective it will be. The further a wing is allowed to rise before taking corrective action, the more airplane surface is exposed to the force of the crosswind. This diminishes the effectiveness of the aileron. Hydroplaning. Hydroplaning is a condition that can exist when an airplane is landed on a runway surface contaminated with standing water, slush, and/or wet snow. Hydroplaning can have serious adverse effects on ground controllability and braking efficiency. The three basic types of hydroplaning are dynamic hydroplaning, reverted rubber hydroplaning, and viscous hydroplaning. Any one of these three can render an airplane partially or totally uncontrollable anytime during the landing roll. Dynamic hydroplaning. Dynamic hydroplaning is a relatively high-speed phenomenon that occurs when there is a film of water on the runway that is at least 1/10 inch deep. As the speed of the airplane and the depth of the water increase, the water layer builds up an increasing resistance to displacement, resulting in the formation of a wedge of water beneath the tire. At some speed, termed the hydroplaning speed, VP, the water pressure equals the weight of the airplane and the tire is lifted off the runway surface. In this condition, the tires no longer contribute to directional control and braking action is nil. Dynamic hydroplaning is related to tire inflation pressure. Data obtained during hydroplaning tests have shown that the minimum dynamic hydroplaning speed, VP, of a tire to be 8.6 times the square root of the tire pressure in pounds per square inch, PSI. For an airplane with a main tire pressure of 24 pounds, the calculated hydroplaning speed would be approximately 42 knots. This is important to note that the calculated speed referred to above is for the start of dynamic hydroplaning. Once hydroplaning has started, it may persist to a significantly slower speed depending on the type being experienced. Reverted rubber hydroplaning. Reverted rubber, steam hydroplaning, occurs during heavy braking that results in a prolonged locked-wheeled skid. Only a thin film of water on the runway is required to facilitate this type of hydroplaning. The tire skidding generates enough heat to cause the rubber to contact with the runway to revert to its original uncured state. The reverted rubber acts as a seal between the tire and the runway, and delays the water exit from the tire footprint area. The water heats and is converted to steam, which supports the tire off the runway. Reverted rubber hydroplaning frequently follows an encounter with dynamic hydroplaning, during which time the pilot may have the brakes locked in an attempt to slow the airplane. Eventually, the airplane slows enough to where the tires make contact with the runway surface and the airplane begins to skid. The remedy for this type of hydroplane is for the pilot to release the brakes and allow the wheels to spin up and apply moderate braking. Reverted rubber hydroplaning is insidious in that the pilot may not know when it begins, and it can persist to very slow ground speeds, 20 knots or less. Viscous hydroplaning. Viscous hydroplaning is due to the viscous properties of water. A thin film of fluid, no more than 1/1000th of an inch in depth, is all that is needed. The tire cannot penetrate the fluid, and the tire rolls on top of the film. This can occur at much slower speed than dynamic hydroplane, but requires a smooth or smooth-acting surface such as asphalt or a touchdown area coated with accumulated rubber of past landings. Such a surface can have the same coefficient of friction as wet ice. When confronted with the possibility of hydroplaning, it is best to land on a grooved runway if available. Touchdown speed should be as slow as possible, consistent with safety. After the nose wheel is lowered to the runway, moderate braking should be applied. If deceleration is not detected and hydroplaning is suspected, the nose should be raised and aerodynamic drag utilized to decelerate to a point where the brakes do become effective. Proper braking technique is essential. The brakes should be applied firmly until reaching a point just short of a skid. At the first sign of a skid, the pilot should release brake pressure and allow the wheels to spin up. Directional control should be maintained as far as possible with the rudder. Remember that in a crosswind, if hydroplaning should occur, the crosswind will cause the airplane to simultaneously weather vane into the wind as well as slide downwind. End of Chapter 8.
Chapter 9 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 9. Performance Maneuvers. Performance maneuvers are used to develop a high degree of pilot skill. They aid the pilot in analyzing the forces acting on the airplane and in developing a fine control touch, coordination, timing, and division of attention for precise maneuvering of the airplane. Performance maneuvers are termed advanced maneuvers because the degree of skill required for proper execution is normally not acquired until a pilot has obtained a sense of orientation and control feel in normal maneuvers. An important benefit of performance maneuvers is the sharpening of fundamental skills to the degree that the pilot can cope with unusual or unforeseen circumstances occasionally encountered in normal flight. Advanced maneuvers are variations and/or combinations of basic maneuvers previously learned. They embody the same principles and techniques as the basic maneuvers, but require a higher degree of skill for proper execution. The student, therefore, who demonstrates a lack of progress in the performance of advanced maneuvers is more than likely deficient in one or more of the basic maneuvers. The flight instructor should consider breaking the advanced maneuver down into its component basic maneuvers in an attempt to identify and correct the deficiency before continuing with the advanced maneuver. Steep turns. The objective of the maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the airplane is near its performance limits. Smoothness of control use, coordination, and accuracy of execution are the important features of this maneuver. The steep turn maneuver consists of a turn in either direction using a bank angle between 45 to 60 degrees. This will cause an overbanking tendency during which maximum turning performance is attained and relatively high load factors are imposed. Because of the high load factors imposed, these turns should be performed at an airspeed that does not exceed the airplane's designed maneuvering speed, VA. The principles of an ordinary steep turn apply, but as a practice maneuver, the steep turns should be continued until 360 degrees or 720 degrees of turn have been completed. See Figure 9-1. An airplane's maximum turning performance is its fastest rate of turn and its shortest radius of turn, which change both airspeed and angle of bank. Each airplane's turning performance is limited by the amount of power its engine is developing, its limited load factor, structural strength, and its aerodynamic characteristics. The limiting load factor determines the maximum bank, which can be maintained without stalling or exceeding the airplane's structural limitations. In most small airplanes, the maximum bank has been found to be approximately 50 degrees to 60 degrees. The pilot should realize the tremendous additional load that is imposed on an airplane as the bank is increased beyond 45 degrees. During a coordinated turn with a 70-degree bank, a load factor of approximately 3 Gs is placed on the airplane structure. Most general aviation type airplanes are stressed for approximately 3.8 Gs. Regardless of the airspeed or the type of airplanes involved, a given angle of bank in a turn, during which altitude is maintained, will always produce the same load factor. Pilots must be aware that an additional load factor increases the stalling speed at a significant rate. Stalling speed increases with the square root of the load factor. For example, a light airplane that stalls at 60 knots in level flight will stall at nearly 85 knots in a 60-degree bank. The pilot's understanding and observance of this fact is an indispensable safety precaution for the performance of all maneuvers requiring turns. Before starting the steep turn, the pilot should ensure that the area is clear of other air traffic since the rate of turn will be quite rapid. After establishing the manufacturer's recommended entry speed or design maneuvering speed, the airplane should be smoothly rolled into the selected bank angle between 45 to 60 degrees. As the turn is being established, back elevator pressure should be smoothly increased to increase the angle of attack. This provides the additional wing lift required to compensate for the increasing load factor. After the selected bank angle has been reached, the pilot will find that considerable force is required on the elevator control to hold the airplane in level flight to maintain altitude. Because of this increase in the force applied to the elevators, the load factor increases rapidly as the bank is increased. Additional back elevator pressure increases the angle of attack, which results in an increase in drag. Consequently, power must be added to maintain the entry altitude and airspeed. Eventually, as the bank approaches the airplane's maximum angle, the maximum performance or structural limit is being reached. If this limit is exceeded, the airplane will be subjected to excessive structural loads and will lose altitude or stall. The limit load factor must not be exceeded to prevent structural damage. During the turn, the pilot should not stare at any one object. To maintain altitude as well as orientation requires an awareness of the relative position of the nose, the horizon, the wings, and the amount of bank. The pilot who references the aircraft's turn by watching only the nose will have difficulty holding altitude constant. On the other hand, the pilot who watches the nose, the horizon, and the wings can usually hold altitude within a few feet. If the altitude begins to increase or decrease, relaxing or increasing the back elevator pressure will be required as appropriate. This may also require a power adjustment to maintain the selected airspeed. A small increase or decrease of 1 to 3 degrees of bank angle may be used to control small altitude deviations. All bank angle changes should be done with coordinated use of aileron and rudder. The rollout from the turn should be timed so that the wings reach level flight when the airplane is exactly on the heading from which the maneuver was started. While the recovery is being made, back elevator pressure is gradually released and power reduced, as necessary to maintain the altitude and airspeed. Common errors in performance of steep turns are failure to adequately clear the area, excessive pitch change during entry or recovery, attempts to start recovery prematurely, failure to stop the turn on a precise heading, excessive rudder during recovery resulting in skidding, inadequate power management, inadequate airspeed control, poor coordination, gaining altitude in right turns and or losing altitude in left turns, failure to maintain constant bank angle, disorientation, attempting to perform the maneuver by instrument reference rather than visual reference, failure to scan for other traffic during the maneuver. Steep spiral. The objective of this maneuver is to improve pilot techniques for airspeed control, wind drift control, planning, orientation, and division of attention. The steep spiral is not only a valuable flight training maneuver, but it has practical application in providing a procedure for dissipating altitude while remaining over a selected spot in preparation for landing, especially for emergency forced landings. A steep spiral is a constant gliding turn, during which a constant radius around a point on the ground is maintained. Similar to the maneuver, turns around a point. The radius should be such that the steepest bank will not exceed 60 degrees. Sufficient altitude must be obtained before starting this maneuver so that the spiral may be continued through a series of at least 3 360-degree turns. See Figure 9-2. The maneuver should not be continued below 1,000 feet above the surface unless performing an emergency landing in conjunction with the spiral. Operating the engine at idle speed for a prolonged period during the glide may result in excessive engine cooling or spark plug fouling. The engine should be cleared periodically by briefly advancing the throttle to normal cruise power while adjusting the pitch attitude to maintain a constant airspeed. Preferably, this should be done while headed into the wind to minimize any variation in ground speed and radius of turn. After the throttle is closed and the gliding speed is established, a gliding spiral should be started and a turn of constant radius maintained around a selected spot on the ground. This will require correction for wind drift by steepening the bank on downwind headings and shallowing the bank on upwind headings, just as in the maneuver turns around a point. During the descending spiral, the pilot must judge the direction and speed of the wind at different altitudes and make appropriate changes in the angle of bank to maintain a uniform radius. A constant airspeed should also be maintained throughout the maneuver. Failure to hold the airspeed constant will cause the radius of the turn and necessary angle of bank to vary excessively. On the downwind side of the maneuver, the steeper the bank angle, the lower the pitch attitude must be to maintain a given airspeed. Conversely, on the upwind side, as the bank angle becomes shallower, the pitch attitude must be raised to maintain the proper airspeed. This is necessary because the airspeed tends to change as the bank is changed from shallow to steep to shallow. During practice of the maneuver, the pilot should execute 3 turns and roll out toward a definite object or on a specific heading. During the rollout, smoothness is essential, and the use of controls must be so coordinated that no increase or decrease of speed results when the straight glide is resumed. Common errors in performance of steep spirals are failure to adequately clear the area, failure to maintain constant airspeed, poor coordination resulting in skidding and or slipping, inadequate wind drift correction, failure to coordinate the controls so that no increase, decrease in speed results when straight glide is resumed, failure to scan for other traffic, failure to maintain orientation. Chandelle. The objective of this maneuver is to develop the pilot's coordination, orientation, planning, and accuracy of control during maximum performance flight. A chandelle is a maximum performance climbing turn beginning from approximately straight and level flight and ending at the completion of a precise 180 degrees of turn in wings level, nose high attitude at the minimum controllable airspeed. See Figure 9-3. The maneuver demands that the maximum flight performance of the airplane be obtained. The airplane should gain the most altitude possible for a given degree of bank and a power setting without stalling. Since numerous atmospheric variables beyond control of the pilot will affect the specific amount of altitude gained, the quality of the performance of the maneuver is not judged solely on the altitude gain, but by the pilot's overall proficiency as it pertains to climb performance for the power bank combination used, and to the elements of piloting skill demonstrated. Prior to starting a chandelle, the flaps and gear, if retractable, should be in the up position, power set to cruise condition, and the airspace behind and above clear of other air traffic. The maneuver should be entered from the straight and level flight, or a shallow dive, and at a speed no greater than the maximum entry speed recommended by the manufacturer, in most cases not above the airplane's design maneuvering speed. VA. After the appropriate airspeed and power setting have been established, the chandelle is started by smoothly entering a coordinated turn with an angle of bank appropriate for the airplane being flown. Normally, this angle of bank should not exceed approximately 30 degrees. After the appropriate bank is established, a climbing turn should be started by smoothly applying back elevator pressure to increase the pitch attitude at a constant rate and to attain the highest pitch attitude as 90 degrees of turn is completed. As the climb is initiated in airplanes with fixed pitch propellers, full throttle may be applied, but it is applied gradually so that the maximum allowable RPM is not exceeded. In airplanes with constant speed propellers, power may be left at the normal cruise setting. Once the bank has been established, the angle of bank should remain constant until 90 degrees of turn is completed. Although the degree of bank is fixed during this climbing turn, it may appear to increase and, in fact, actually will tend to increase if allowed to do so as the maneuver continues. When the turn has progressed 90 degrees from the original heading, the pilot should begin rolling out of the bank at a constant rate while maintaining a constant pitch attitude. Since the angle of bank will be decreasing during the rollout, the vertical component of lift will increase slightly. For this reason, it may be necessary to release a slight amount of back elevator pressure in order to keep the nose of the airplane from rising higher. As the wings are being leveled at the completion of 180 degrees of turn, the pitch attitude should be noted by checking the outside references and the attitude indicator. This pitch attitude should be held momentarily while the plane is at the minimum controllable airspeed. Then the pitch attitude may be gently reduced to return to straight and level cruise flight. Since the airspeed is constantly decreasing throughout the maneuver, the effects of engine torque become more and more prominent. Therefore, right rudder pressure is gradually increased to control yaw and maintain a constant rate of turn and to keep the airplane in coordinated flight. The pilot should maintain coordinated flight by the feel of pressures being applied on the controls and by the ball instrument of the turn and slip indicator. If coordinated flight is being maintained, the ball will remain in the center of the race. To roll out of a left chandelle, the left aileron must be lowered to raise the left wing. This creates more drag than the aileron on the right wing, resulting in the tendency for the airplane to yaw to the left. With the low airspeed at this point, torque effect tries to make the airplane yaw to the left even more. Thus, there are two forces pulling the airplane's nose to the left: aileron drag and torque. To maintain coordinated flight, considerable right rudder pressure is required during the rollout to overcome the effects of aileron drag and torque. In a chandelle to the right, when control pressure is applied to begin the rollout, the aileron on the right wing is lowered. This creates more drag on that wing and tends to make the airplane yaw to the right. At the same time, the effect of torque at the lower speed is causing the airplane's nose to yaw to the left. Thus, aileron drag pulling the nose to the right and torque pulling to the left tend to neutralize each other. If excessive left rudder pressure is applied, the rollout will be uncoordinated. The rollout to the left can usually be accomplished with very little left rudder, since the effects of aileron drag and torque tend to neutralize each other. Releasing some right rudder, which has been applied to correct for torque, will normally give the same effect as applying left rudder pressure. When the wings become level and the ailerons are neutralized, the aileron drag disappears. Because of the low airspeed and high power, the effects of torque become the more prominent force and must continue to be controlled with rudder pressure. A rollout to the left is accomplished mainly by applying aileron pressure. During the rollout, right rudder pressure should be gradually released, and the left rudder applied only as necessary to maintain coordination. Even when the wings are level and aileron pressure is released, right rudder pressure must be held to counteract torque and hold the nose straight. Common errors in performance of chandelles are: failure to adequately clear the area, too shallow an initial bank resulting in a stall, too steep an initial bank, resulting in failure to gain maximum performance. Allowing the actual bank to increase after establishing initial bank angle. Failure to start the recovery at the 90-degree point in the turn. Allowing the pitch attitude to increase as the bank is rolled out during the second 90-degree of turn. Removing all of the bank before the 180-degree point is reached. Nose low on recovery, resulting in too much airspeed. Control roughness. Poor coordination, slipping or skidding. Stalling at any point during the maneuver. Execution of a steep turn instead of a climbing maneuver. Failure to scan for other aircraft. Attempting to perform the maneuver by instrument reference rather than visual reference. Lazy 8. The Lazy 8 is a maneuver designed to develop perfect coordination of controls through a wide range of airspeeds and altitudes so that certain accuracy points are reached with planned attitude and airspeed. In its execution, the dive, climb, and turn are all combined, and the combinations are varied and applied throughout the performance range of the airplane. It is the only standard flight training maneuver during which at no time do the forces on the controls remain constant. The Lazy 8 as a training maneuver has great value since constantly varying forces and attitudes are required. These forces must be constantly coordinated due not only to the changing combination of banks, dives, and climbs, but also to constantly varying airspeed. The maneuver helps develop subconscious feel, planning, orientation, coordination, and speed sense. It is not possible to do a Lazy 8 mechanically because the control pressures required for perfect coordination are never exactly the same. This maneuver derives its name from the manner in which the extended longitudinal axis of the airplane is made to trace a flight pattern in the form of a figure 8 lying on its side. A Lazy 8. See Figure 9-4. A Lazy 8 consists of two 180-degree turns in opposite directions while making a climb and a descent in a symmetrical pattern during each of the turns. At no time throughout the Lazy 8 is the airplane flown straight and level. Instead, it is rolled directly from one bank to the other with the wings level only at the moment the turn is reversed, the completion of each 180-degree change in heading. As an aid for making symmetrical loops of the 8 during each turn, prominent reference points should be selected on the horizon. The reference point selected should be 45 degrees, 90 degrees, and 135 degrees from the direction in which the maneuver is begun. Prior to performing a Lazy 8, the airspace behind and above should be clear of other air traffic. The maneuver should be entered from the straight and level flight at normal cruise power and at an airspeed recommended by the manufacturer or at the airplane's design maneuvering speed. The maneuver is started from level flight with a gradual climbing turn in the direction of the 45-degree reference point. The climbing turn should be planned and controlled so that the maximum pitch up attitude is reached at the 45-degree point. The rate of rolling into the bank must be such as to prevent the rate of turn from becoming too rapid. As the pitch attitude is raised, the airspeed decreases, causing the rate of turn to increase. Since the bank also is being increased, it too causes the rate of turn to increase. Unless the maneuver is begun with a slow rate of roll, the combination of increasing pitch and increasing bank will cause the rate of turn to be so rapid that the 45-degree reference point will be reached before the highest pitch attitude is attained. At the 45-degree point, the pitch attitude should be at maximum and the angle of bank continuing to increase. Also, at the 45-degree point, the pitch attitude should start to decrease slowly toward the horizon and the 90-degree reference point. Since the airspeed is still decreasing, right rudder pressure will have to be applied to counteract torque. As the airplane's nose is being lowered toward the 90-degree reference point, the bank should continue to increase. Due to the decreasing airspeed, a slight amount of opposite aileron pressure may be required to prevent the bank from becoming too steep. When the airplane completes 90 degrees of the turn, the bank should be at the maximum angle, approximately 30 degrees, the airspeed should be at its minimum, 5 to 10 knots above stall speed, and the airplane pitch attitude should be passing through level flight. It is at this time that an imaginary line extending from the pilot's eye and parallel to the longitudinal axis of the airplane passes through the 90-degree reference point. Lazy 8s normally should be performed with no more than approximately a 30-degree bank. Steeper banks may be used, but control touch and technique must be developed to a much higher degree than when the maneuver is performed with a shallower bank. The pilot should not hesitate at this point, but should continue to fly the airplane into a descending turn so that the airplane's nose describes the same size loop below the horizon as it did above. As the pilot's reference line passes through the 90-degree point, the bank should be decreased gradually and the airplane's nose allowed to continue lowering. When the airplane has turned 135 degrees, the nose should be in its lowest pitch attitude. The airspeed will be increasing during this descending turn, so it will be necessary to gradually relax rudder and aileron pressure and to simultaneously raise the nose and roll the wings level. As this is being accomplished, the pilot should note the amount of turn remaining and adjust the rate of rollout and pitch change so that the wings become level and the original airspeed is attained in level flight just as the 180-degree point is reached. Upon returning to starting altitude and the 180-degree point, a climbing turn should be started immediately in the opposite direction toward the selected reference points to complete the second half of the 8 in the same manner as the first half. See Figure 9-5. Due to the decreasing airspeed, considerable right rudder pressure is gradually applied to counteract torque at the top of the 8 in both the right and left turns. The pressure will be greatest at the point of lowest airspeed. More right rudder pressure will be needed during the climbing turn to the right than in the turn to the left because more torque correction is needed to prevent yaw from decreasing the rate of turn. In the left climbing turn, the torque will tend to contribute to the turn. Consequently, less rudder pressure is needed. It will be noted that the controls are slightly crossed in the right climbing turn because of the need for left aileron pressure to prevent overbanking and right rudder to overcome torque. The correct power setting for the Lazy 8 is that which will maintain the altitude for the maximum and minimum airspeeds used during the climbs and descents of the 8. Obviously, if excess power were used, the airplane would have gained altitude when the maneuver is completed. If insufficient power were used, altitude would have been lost. Common errors in performance of Lazy 8s are failure to adequately clear the area, using the nose or top of engine cowl instead of the true longitudinal axis resulting in unsymmetrical loops, watching the airplane instead of the reference points, inadequate planning resulting in the peaks of the loops both above and below the horizon not coming in the proper place, control roughness, usually caused by attempts to counteract poor planning. Persistent gain or loss of altitude with the completion of each 8. Attempting to perform the maneuver rhythmically, resulting in poor pattern symmetry. Allowing the airplane to fall out of the tops of the loops rather than flying the airplane through the maneuver. Slipping and or skidding. Failure to scan for other traffic. End of Chapter 9. Recording by Dale Latham.
Chapter 10 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Chapter 10, Night Operations. Night Vision. Generally, most pilots are poorly informed about night vision. Human eyes never function as effectively at night as the eyes of animals with nocturnal habits. But if humans learn how to use their eyes correctly and know their limitations, night vision can be improved significantly. There are several reasons for training to use the eyes correctly. One reason is the mind and eyes act as a team for a person to see well. Both team members must be used effectively. The construction of the eyes is such that to see at night they are used differently than during the day. Therefore, it is important to understand the eye's construction and how the eye is affected by darkness. Innumerable light-sensitive nerves called cones and rods are located at the back of the eye or retina, a layer upon which all images are focused. These nerves connect to the cells of the optic nerve, which transmits messages directly to the brain. The cones are located in the center of the retina, and the rods are concentrated in a ring around the cones. See Figure 10-1. The function of the cones is to detect color, details, and faraway objects. The rods function when something is seen out of the corner of the eye or peripheral vision. They detect objects, particularly those that are moving, but do not give detail or color, only shades of gray. Both the cones and the rods are used for vision during daylight. Although there is not a clear-cut division of function, the rods make night vision possible. The rods and cones function in daylight and in moonlight, but in the absence of normal light, the process of night vision is placed almost entirely on the rods. The fact that rods are distributed in a band around the cones and do not lie directly behind the pupils makes off-center viewing, looking to one side of an object, important during night flight. During daylight, an object can be seen best by looking directly at it, but at night, a scanning procedure to permit off-center viewing of the object is more effective. Therefore, the pilot should consciously practice this scanning procedure to improve night vision. The eye's adaptation to darkness is another important aspect of night vision. When a dark room is entered, it is difficult to see anything until the eyes become adjusted to the darkness. Most everyone has experienced this after entering a darkened movie theater. In this process, the pupils of the eyes first enlarge to receive as much of the available light as possible. After approximately 5 to 10 minutes, the cones become adjusted to the dim light, and the eyes become 100 times more sensitive to the light than they were before the dark room was entered. Much more time, about 30 minutes, is needed for the rods to become adjusted to darkness. But when they do adjust, they are about 100,000 times more sensitive to light than they were in the lighted area. After the adaptation process is complete, much more can be seen, especially if the eyes are used correctly. After the eyes have adapted to the dark, the entire process is reversed when entering a lighted room. The eyes are first dazzled by the brightness, but become completely adjusted in a very few seconds, thereby losing their adaptation to the dark. Now, if the dark room is re-entered, the eyes again go through the long process of adapting to the darkness. The pilot before and during night flight must consider the adaptation process of the eyes. First, the eyes should be allowed to adapt to the low level of light, and then they should be kept adapted. After the eyes have become adapted to the darkness, the pilot should avoid exposing them to any bright white light that will cause temporary blindness and could result in serious consequences. Temporary blindness caused by an unusually bright light may result in illusions or after images until the eyes recover from the brightness. The brain creates these illusions reported by the eyes. This results in misjudging or incorrectly identifying objects, such as mistaking slanted clouds for the horizon or populated areas for a landing field. Vertigo is experienced as a feeling of dizziness and imbalance that can create or increase illusions. The illusions seem very real, and pilots at every level of experience and skill can be affected. Recognizing that the brain and eyes can play tricks in this manner is the best protection for flying at night. Good eyesight depends upon physical condition. Fatigue, colds, vitamin deficiency, alcohol, stimulants, smoking, or medication can seriously impair vision. Keeping these facts in mind and taking adequate precautions should safeguard night vision. In addition to the principles previously discussed, the following items will aid in increasing night vision effectiveness. Adapt the eyes to darkness prior to flight and keep them adapted. About 30 minutes is needed to adjust the eyes to maximum efficiency after exposure to a bright light. If oxygen is available, use it during night flying. Keep in mind that a significant deterioration in night vision can occur at cabin altitudes as low as 5,000 feet. Close one eye when exposed to bright light to help avoid the blinding effect. Do not wear sunglasses after sunset. Move the eyes more slowly than in daylight. Blink the eyes if they become blurred. Concentrate on seeing objects. Force the eyes to view off-center. Maintain good physical condition. Avoid smoking, drinking, and using drugs that may be harmful. Night illusions. In addition to night vision limitations, pilots should be aware that night illusions could cause confusion and concerns during night flying. The following discussion covers some of the common situations that cause illusions associated with night flying. On a clear night, distant stationary lights can be mistaken for stars or other aircraft. Even the northern lights can confuse a pilot and indicate a false horizon. Certain geometrical patterns of ground lights, such as a freeway, runway, approach, or even lights on a moving train, can cause confusion. Dark nights tend to eliminate reference to a visual horizon. As a result, pilots need to rely less on outside references at night and more on flight and navigation instruments. Visual autokinesis can occur when a pilot stares at a single light source for several seconds on a dark night. The result is that the light will appear to be moving. The autokinesis effect will not occur if the pilot expands the visual field. It is a good procedure not to become fixed on one source of light. Distractions and problems can result from a flickering light in the cockpit, anti-collision light, strobe lights, or other aircraft lights, and can cause flicker vertigo. If continuous, the possible physical reactions can be nausea, dizziness, grogginess, unconsciousness, headaches, or confusion. The pilot should try to eliminate any light source causing blinking or flickering problems in the cockpit. A black hole approach occurs when the landing is made from over water or non-lighted terrain, where the runway lights are the only source of light. Without peripheral visual cues to help, pilots will have trouble orientating themselves relative to Earth. The runway can seem out of position, downsloping or upsloping, and in the worst case, results in landing short of the runway. If an electronic glide slope or visual approach slope indicator, VASI, is available, it should be used. If navigation aids, nav aids, are unavailable, careful attention should be given to using the flight instruments to assist in maintaining orientation and a normal approach. If at any time the pilot is unsure of his or her position or attitude, a go-around should be executed. Bright runway and approach lighting systems, especially where few lights illuminate the surrounding terrain, may create the illusion of less distance to the runway. In this situation, the tendency is to fly a higher approach. Also, when flying over terrain with only a few lights, it will make the runway recede or appear farther away. With this situation, the tendency is common to fly a lower than normal approach. If the runway has a city in the distance, on higher terrain, the tendency will be to fly a lower than normal approach. A good review of the airfield layout and boundaries before initiating any approach will help the pilot maintain a safe approach angle. Illusions created by runway lights result in a variety of problems. Bright lights or bold colors advance the runway, making it appear closer. Night landings are further complicated by the difficulty of judging distance and the possibility of confusing approach and runway lights. For example, when a double row of approach lights joins the boundary lights of the runway, there can be confusion where the approach lights terminate and runway lights begin. Under certain conditions, approach lights can make the aircraft seem higher in a turn to final than when its wings are level. Pilot equipment. Before beginning a night flight, carefully consider personal equipment that should be readily available during the flight. At least one reliable flashlight is recommended as standard equipment on all night flights. Remember to place a spare set of batteries in the flight kit. A D-cell size flashlight with a bulb switching mechanism that can be used to select white or red light is preferable. The white light is used while performing the pre-flight visual inspection of the airplane, and the red light is used when performing cockpit operations. Since the red light is non-glaring, it will not impair night vision. Some pilots prefer 2 flashlights, one with a white light for pre-flight and the other a pen light type with a red light. The latter can be suspended by a string from around the neck to ensure the light is always readily available. One word of caution. If a red light is used for reading an aeronautical chart, the red features of the chart will not show up. Aeronautical charts are essential for night cross-country flight, and if the intended course is near the edge of the chart, the adjacent chart should also be available. The lights of cities and towns can be seen at surprising distances at night, and if this adjacent chart is not available to identify those landmarks, confusion could result. Regardless of the equipment used, organization of the cockpit eases the burden on the pilot and enhances safety. Airplane equipment and lighting. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, specifies the basic minimum airplane equipment required for night flight. This equipment includes only basic instruments, lights, electrical energy source, and spare fuses. The standard instruments required for instrument flight under 14 CFR Part 91 are a valuable asset for aircraft control at night. An anti-collision light system, including a flashing or rotating beacon and position lights, is required airplane equipment. Airplane position lights are arranged similar to those of boats and ships. A red light is positioned on the left wingtip, a green light on the right wingtip, and a white light on the tail. See Figure 10-2. This arrangement provides a means by which pilots can determine the general direction of movement of other airplanes in flight. If both the red and green light of another aircraft were observed, the airplane would be flying toward the pilot and could be on a collision course. Landing lights are not only useful for taxi, takeoffs, and landings, but also provide a means by which airplanes can be seen at night by other pilots. The Federal Aviation Administration, FAA, has initiated a voluntary pilot safety program called Operation Lights On. The Lights On idea is to enhance the see and be seen concept of averting collisions both in the air and on the ground, and to reduce the potential for bird strikes. Pilots are encouraged to turn on their landing lights when operating within 10 miles of an airport. This is for both day and night or in conditions of reduced visibility. This should also be done in areas where flocks of birds may be expected. Although turning on aircraft lights supports the see and be seen concept, pilots should not become complacent about keeping a sharp lookout for other aircraft. Most aircraft lights blend in with the stars or the lights of the cities at night and go unnoticed unless a conscious effort is made to distinguish them from other lights. Airport and navigation lighting aids. The lighting systems used for airports, runways, obstructions, and other visual aids at night are other important aspects of night flying. Lighted airports located away from congested areas can be identified readily at night by the lights outlining the runways. Airports located near or within large cities are often difficult to identify in the maze of lights. It is important not only to know the exact location of an airport relative to the city, but also to be able to identify these airports by the characteristics of their lighting pattern. Aeronautical lights are designed and installed in a variety of colors and configurations, each having its own purpose. Although some lights are used only during low ceiling and visibility conditions, this discussion includes only the lights that are fundamental to visual flight rules, VFR, night operation. It is recommended that prior to a night flight, and particularly a cross-country night flight, the pilot check the availability and status of lighting systems at the destination airport. This information can be found on aeronautical charts and in the airport/facility directory. The status of each facility can be determined by reviewing pertinent Notices to Airmen, NOTAMs. A rotating beacon is used to indicate the location of most airports. The beacon rotates at a constant speed, thus producing what appears to be a series of light flashes at regular intervals. These flashes may be one or two different colors that are used to identify various types of landing areas. For example, lighted civilian land airports, alternating white and green. Lighted civilian water airports, alternating white and yellow. Lighted military airports, alternating white and green but are differentiated from civil airports by dual-peaked, too quick, white flashes, then green. Beacons producing red flashes indicate obstructions or areas considered hazardous to aerial navigation. Steady burning red lights are used to mark obstructions on or near airports and sometimes to supplement flashing lights on en route obstructions. High-intensity flashing white lights are used to mark some supporting structures of overhead transmission lines that stretch across rivers, chasms, and gorges. These high-intensity lights are also used to identify tall structures such as chimneys and towers. As a result of the technological advancements in aviation, runway lighting systems have become quite sophisticated to accommodate takeoffs and landings in various weather conditions. However, the pilot whose flying is limited to VFR only needs to be concerned with the following basic lighting of runways and taxiways. The basic runway lighting system consists of two straight parallel lines of runway edge lights defining the lateral limits of the runway. These lights are aviation white, although aviation yellow may be substituted for a distance of 2,000 feet from the far end of the runway to indicate a caution zone. At some airports, the intensity of the runway edge lights can be adjusted to satisfy the individual needs of the pilot. The length limits of the runway are defined by straight lines of lights across the runway ends. At some airports, the runway threshold lights are aviation green, and the runway end lights are aviation red. At many airports, the taxiways are also lighted. A taxiway edge lighting system consists of blue lights that outline the usable limits of taxi paths. Preparation and pre-flight. Night flying requires that pilots be aware of and operating within their abilities and limitations. Although careful planning of any flight is essential, night flying demands more attention to the details of pre-flight preparation and planning. Preparation for a night flight should include a thorough review of the available weather reports and forecasts, with particular attention given to temperature dew point spread. A narrow temperature dew point spread may indicate the possibility of ground fog. Emphasis should also be placed on wind direction and speed, since its effect on the airplane cannot be as easily detected at night as during the day. On night cross-country flights, appropriate aeronautical charts should be selected, including the appropriate adjacent charts. Course lines should be drawn in black to be more distinguishable. Prominently lighted checkpoints along the prepared course should be noted. Rotating beacons at airports, lighted obstructions, lights of cities or towns, and lights from major highway traffic all provide excellent visual checkpoints. The use of radio navigation aids and communication facilities adds significantly to the safety and efficiency of night flying. All personal equipment should be checked prior to flight to ensure proper functioning. It is very disconcerting to find at the time of need that a flashlight, for example, does not work. All airplane lights should be turned on momentarily and checked for operation. Position lights can be checked for loose connections by tapping the light fixture. If the lights blink while being tapped, further investigation to determine the cause should be made prior to flight. The parking ramp should be examined prior to entering the airplane. During the day, it is quite easy to see step ladders, chuck holes, wheel chocks, and other obstructions. But at night, it is more difficult. A check of the area can prevent taxiing mishaps. Starting, taxiing, and run-up. After the pilot is seated in the cockpit and prior to starting the engine, all items and materials to be used on the flight should be arranged in such a manner that they will be readily available and convenient to use. Extra caution should be taken at night to assure the propeller area is clear. Turning the rotating beacon on or flashing the airplane position lights will serve to alert persons nearby to remain clear of the propeller. To avoid excessive drain of electrical current from the battery, it is recommended that the unnecessary electrical equipment be turned off until after the engine has been started. After starting and before taxiing, the taxi or landing light should be turned on. Continuous use of the landing light with RPM power settings normally used for taxiing may place an excessive drain on the airplane's electrical system. Also, overheating of the landing light could become a problem because of inadequate airflow to carry the heat away. Landing lights should be used as necessary while taxiing. When using landing lights, consideration should be given to not blinding other pilots. taxi slowly, particularly in congested areas. If taxi lines are painted on the ramp or taxiway, these lines should be followed to ensure a proper path along the route. The before takeoff and run-up should be performed using the checklist. During the day, forward movement of the airplane can be detected easily. At night, the airplane could creep forward without being noticed unless the pilot is alert for this possibility. Hold or lock the brakes during the run-up and be alert for any forward movement. Takeoff and climb. Night flying is very different from day flying and demands more attention of the pilot. The most noticeable difference is the limited availability of outside visual references. Therefore, flight instruments should be used to a greater degree in controlling the airplane. This is particularly true on night takeoffs and climbs. The cockpit light should be adjusted to a minimum brightness that will allow the pilot to read the instruments and switches and yet not hinder the pilot's outside vision. This will also eliminate light reflections on the windshield and windows. After ensuring that the final approach and runway are clear of other air traffic, or when cleared for takeoff by the tower, the landing lights and taxi lights should be turned on, and the airplane lined up with the center line of the runway. If the runway does not have centerline lighting, use the painted centerline and the runway edge lights. After the airplane is aligned, the heading indicator should be noted or set to correspond to the known runway direction. To begin the takeoff, the brake should be released and the throttle smoothly advanced to maximum allowable power. As the airplane accelerates, it should be kept moving straight ahead, between and parallel to the runway edge lights. The procedure for night takeoffs is the same as for normal daytime takeoffs, except that many of the runway visual cues are not available. Therefore, the flight instruments should be checked frequently during the takeoff to ensure the proper pitch attitude, heading, and airspeed are being attained. As the airspeed reaches the normal liftoff speed, the pitch attitude should be adjusted to that which will establish a normal climb. This should be accomplished by referring to both outside visual references, such as lights, and to the flight instruments. See Figure 10-3. After becoming airborne, the darkness of night often makes it difficult to note whether the airplane is getting closer to or farther from the surface. To ensure the airplane continues in a positive climb, be sure a climb is indicated on the attitude indicator, vertical speed indicator, VSI, and altimeter. It is also important to ensure the airspeed is at best climb speed. Necessary pitch and bank adjustments should be made by referencing the attitude and heading indicators. It is recommended that turns not be made until reaching a safe maneuvering altitude. Although the use of landing lights provides help during the takeoff, they become ineffective after the airplane has climbed to an altitude where the light beam no longer extends to the surface. The light can cause distortion when it is reflected by haze, smoke, or fog that might exist in the climb. Therefore, when the landing light is used for the takeoff, it may be turned off after the climb is well established, provided other traffic in the area does not require its use for collision avoidance. Orientation and navigation. Generally, at night, it is difficult to see clouds and restrictions to visibility, particularly on dark nights or under overcast. The pilot flying under VFR must exercise caution to avoid flying into clouds or a layer of fog. Usually, the first indication of flying into restricted visibility conditions is the gradual disappearance of lights on the ground. If the lights begin to take on an appearance of being surrounded by a halo or glow, the pilot should use caution in attempting further flight in that same direction. Such a halo or glow around lights on the ground is indicative of ground fog. Remember that if a descent must be made through fog, smoke, or haze in order to land, the horizontal visibility is considerably less when looking through the restriction than it is when looking straight down through it from above. Under no circumstances should a VFR night flight be made during poor or marginal weather conditions, unless both the pilot and aircraft are certified and equipped for Flight Under Instrument Flight Rules, IFR. The pilot should practice and acquire competency in straight and level flight, climbs and descents, level turns, climbing and descending turns, and steep turns. Recovery from unusual attitudes should also be practiced, but only on dual flights with a flight instructor. The pilot should also practice these maneuvers with all the cockpit lights turned off. This blackout training is necessary if the pilot experiences an electrical or instrument light failure. Training should also include using the navigation equipment and local nav aids. In spite of fewer references or checkpoints, night cross-country flights do not present particular problems if pre-planning is adequate, and the pilot continues to monitor position, time estimates, and fuel consumed. Nav aids, if available, should be used to assist in monitoring en route progress. Crossing large bodies of water at night in single-engine airplanes could be potentially hazardous, not only from the standpoint of landing, ditching, in the water, but also because, with little or no lighting, the horizon blends with the water, in which case depth perception and orientation become difficult. During poor visibility conditions over water, the horizon will become obscure and may result in a loss of orientation. Even on clear nights, the stars may be reflected on the water's surface, which could appear as a continuous array of lights, thus making the horizon difficult to identify. Lighted runways, buildings, or other objects may cause illusions to the pilot when seen from different altitudes. At an altitude of 2,000 feet, a group of lights on an object may be seen individually, while at 5,000 feet or higher, the same lights could appear to be one solid light mass. These illusions may become quite acute with altitude changes, and if not overcome, could present problems in respect to approaches to lighted runways. Approaches and landings. When approaching the airport to enter the traffic pattern and land, it is important that the runway lights and other airport lighting be identified as early as possible. If the airport layout is unfamiliar to the pilot, sighting of the runway may be difficult until very close in due to the maze of lights observed in the area. See Figure 10-4. The pilot should fly toward the rotating beacon until the lights outlining the runway are distinguishable. To fly a traffic pattern of proper size and direction, the runway threshold and runway edge lights must be positively identified. Once the airport lights are seen, these lights should be kept in sight throughout the approach. Distance may be deceptive at night due to limited lighting conditions. A lack of intervening references on the ground and the inability of the pilot to compare the size and location of different ground objects cause this. This also applies to the estimation of altitude and speed. Consequently, more dependence must be placed on flight instruments, particularly the altimeter and the airspeed indicator. When entering the traffic pattern, allow for plenty of time to complete the before landing checklist. If the heading indicator contains a heading bug, setting it to the runway heading will be an excellent reference for the pattern legs. Every effort should be made to maintain the recommended airspeeds and execute the approach and landing in the same manner as during the day. A low, shallow approach is definitely inappropriate during a night operation. The altimeter and VSI should be constantly cross-checked against the airplane's position along the base leg and final approach. A visual approach slope indicator, VASI, is an indispensable aid in establishing and maintaining a proper glide path. See Figure 10-5. After turning onto the final approach and aligning the airplane midway between the two rows of runway edge lights, the pilot should note and correct for any wind drift. Throughout the final approach, pitch and power should be used to maintain a stabilized approach. Flaps should be used the same as in a normal approach. Usually, halfway through the final approach, the landing light should be turned on. Earlier use of the landing light may be necessary because of operation lights on or for local traffic considerations. The landing light is sometimes ineffective since the light beam will usually not reach the ground from higher altitudes. The light may even be reflected back into the pilot's eyes by an existing haze, smoke, or fog. This disadvantage is overshadowed by the safety considerations provided by using the Operation Lights On procedure around other traffic. The round out and touchdown should be made in the same manner as in day landings. At night, the judgment of height, speed, and sink rate is impaired by the scarcity of observable objects in the landing area. The inexperienced pilot may have a tendency to round out too high until attaining familiarity with the proper height for the correct round out. To aid in determining the proper round out point, continue a constant approach descent until the landing lights reflect on the runway and tire marks on the runway can be seen clearly. At this point, the roundout should be started smoothly and the throttle gradually reduced to idle as the airplane is touching down. See Figure 10-6. During landings, without the use of landing lights, the roundout may be started when the runway lights at the far end of the runway first appear to be rising higher than the nose of the airplane. This demands a smooth and very timely roundout and requires that the pilot feel for the runway surface using power and pitch changes as necessary for the airplane to settle slowly to the runway. Blackout landings should always be included in night pilot training as an emergency procedure. Night emergencies. Perhaps the pilot's greatest concern about flying a single-engine airplane at night is the possibility of a complete engine failure and the subsequent emergency landing. This is a legitimate concern, even though continuing flight into adverse weather and poor pilot judgment account for most serious accidents. If the engine fails at night, several important procedures and considerations to keep in mind are: maintain positive control of the airplane and establish the best glide configuration and airspeed. Turn the airplane towards an airport or away from congested areas. Check to determine the cause of the engine malfunction, such as the position of fuel selectors, magneto switch, or primer. If possible, the cause of the malfunction should be corrected immediately and the engine restarted. Announce the emergency situation to Air Traffic Control, ATC, or Unicom. If already in radio contact with a facility, do not change frequencies unless instructed to change. If the condition of the nearby terrain is known, turn towards an unlighted portion of the area. Plan an emergency approach to an unlighted portion. Consider an emergency landing area close to public access if possible. This may facilitate rescue or help if needed. Maintain orientation with the wind to avoid a downwind landing. Complete the before landing checklist and check the landing lights for operation at altitude and turn on in sufficient time to illuminate the terrain or obstacles along the flight path. The landing should be completed in the normal landing attitude and the slowest possible airspeed. If the landing lights are unusable and outside visual references are not available, the airplane should be held in level landing attitude until the ground is contacted. After landing, turn off all switches and evacuate the airplane as quickly as possible. End of Chapter 10. End of Volume 1 of the Airplane Flying Handbook FAA-H-8083-3A by the Federal Aviation Administration.